Now, previously we talked about principle of work and energy. Today we talk at the last chapter or last session of the chapter 7, which is conservation of energy. So conservation of energy will be the same as particles. You only need to take note that usually if you can't find any parameter from the principle of work and energy, you add on conservation of energy in your solution. So you have one more equation to solve. Okay, right. So because when you apply conservation of energy, the force that inside your free body diagram, they are independent of the path. So you no longer see the distance traveled and all this, right? So only dependent on initial and final position of the body. So what happened before equal to what happened after. Okay. Okay. So I need to highlight the potential energy. When we talk about energy, kinetic we already covered in the principle of energy and work and energy. But when it comes to conservation of energy, we need to consider another type of energy, which is potential energy. So this one, you see this diagram in the particles already, right? So above datum, you get positive, mgh. Below datum, you get negative. So this is energy lah. Okay, all right. Okay, then another one is a spring. Spring half ks square for spring, right? So the equation to be used for spring is half ks square. Okay. Then when we use conservation of energy, we look at what happened to the potential and kinetics. So kinetics is half mv square plus the initial moment I omega square, right? Then if we have a potential energy, then we look at whether it is the change of position. Position means mgh already lah, the potential energy. Or you see spring, then you need to calculate spring already. Half kx square. Okay. All right. So previously we write the work conserved equal to potential before minus after, right? So the full equation for principle of work and energy, if you want to go for full, then kinetic plus potential plus work, this is non-conservative, equal to kinetic plus potential. Okay, so energy, work, and energy. Okay, right. So this is non-conservative force like friction. So if you have friction, then normally you see this one. Okay. Then at the end, we will refer to kinetic plus potential before equal to after. This equation we refer as conservation of mechanical energies. Okay. So when you use this conservation of energy, we only look at conservative force only. Okay. So for example, friction, we will ignore, drag will ignore. Okay, so this one, friction and drag, they are non-conservative. So you don't need to calculate their effect in the energy, right? Okay. Okay. Right. So we look at example 5. So example 5, you look at the question, you already know with the G point, you know this is rigid body question. You see spring, you know that you need to use spring equation. Spring have two, one is work, one is energy. Work is force times the distance traveled, but energy also half kx squared. Then this one, what is the motion of A? Because this is a move in the straight line, linear, right? So linear. So when you move A will move left or right. So the vector of velocity will be left or right only. Same with B. B can only move up and down, but with velocity move up and down. Okay. Then when the rod AB, you just estimate the motion. So it depends on the spring whether if B move down, and then it release, this one will rotate anti-clockwise. Make sense? If you pull B, then you let go, B will move up, right? B will move up because of the spring. Then the arm AB will swing anti-clockwise. Okay. So you look at the statement. The mass of AB was given. So you know that the focus is on AB. And AB is a rod. So in the table for second moment inertia, you look for the rod. Okay. Then it's confined at the end move horizontal vertical slot. Spring have stiffness K and is unstretched when theta equals 0. So theta is here. So when theta 0 is like this. Okay. So you know that when it unstretched is this one, but the diagram show you longer. So you need to continue to read lah. Determine the angular velocity, which is omega of this rod. When theta 0, if the rod is released from rest when theta 30 degree, means before you start, you already stretch this one, right? Release from rest when theta equal 30 degree. So you need to find when you pull this one up to 30 degree, you know that this is right angle, right? The right angle triangular. So when you pull 30 degree, you can find the distance here, distance here. When you can find the distance here, then you can solve for the unknown lah. Okay, 30 degree, ignore the mass. So the question asks you this rod. Okay, this rod, the angular omega, right? Angular velocity. Now, when you deal with rod, let's say you have point A, point B. And if you have V, okay, let's say you have one lenticular direction, which is VB. When you have BB and you have R, so this one will swing. Let's say A was fixed. So let's say A was fixed. Then you have VB, this one rotate anti-clockwise, right? So this one will give you omega. So when you link R and V, you can use the V equal to omega R to find the missing parameter. So here, you because to need when you want to find the omega angular velocity, you need R, right? R you can find from the distance here. Okay. Then the V you can find from the speed that this one move up. Okay. So and how you find the speed move up? You can either from the energy equation, because energy kinetic give you half mv squared, right? Okay, so free body diagram. So free body diagram, first, again, we are focusing on rod AB. So the rest is just converted to velocity, force, and so on, right? So you just extract rod AB and then go to the point center of gravity, put in W first. Then you start to do datum line. You draw. So this is 0.4. This distance is sine because hypotenuse opposite is sine, right? Then your y1 will be 0.4 sine meter. Okay, so along all this triangular, all the height will be 0.4 sine theta lah. Okay, or here, right? Okay, so this is a general one. So what happens if you have when you reach 0 degree, right? When you reach 0 degree, so 0 degree still your gravitational still have force, still have W, and your datum is here, right? Your datum is here. So the distance traveled is 0 for S2, S2 is 0. Okay, so your S1 is here, S2 is here. S1 is here, S2 is here. Okay, datum always 0. So when you have these two diagrams, then you study the potential energy first. So when rod in position 1, which is here, the center of gravity locate below datum, right? So center of gravity below datum. So below datum is negative. Okay, so gravitational potential energy will be negative for case number 1. Okay. Uh, so for case number 1, your potential will have mgh plus the spring, right? The potential minus because it's below, and the spring will be half ks squared. Right? You already have your S1 equation, right? So you put inside there, right? You put inside over there. So just need to remember here is 0.2. Sorry, typo error in my slides. Y1 should be 0.2, not 0.4. Okay, Y1 equal to 0.2 sine theta, not 0.4. Because it's, you take from here and here. Okay, there's a typo error on my slides. Okay, then okay, this one mgh plus half k is given. K is given. Just need to careful on the unit lah. Sometimes question will give you kilonewton and so on. Right? Just be careful. And then S is here. S1 is here. Because you're referring to spring. One is center of gravity, one is spring. One is the rod, one is this one. Okay. Okay, then you get the potential energy for position number 1. Okay, you repeat the same for second case. Second case, what happened to the mgh? 0. Then your spring also stretch, right? Okay, so for what happened? Okay, so for position what define? Position 2, potential energy 0. And when you return to 0 degree, the question already tell you it was unstretched at 0 degree. So unstretched means no energy, right? So your spring also 0. So at position 2, your potential is 0. Yeah. So you need to read carefully the question. Okay, then the kinetic energy. Kinetic energy, you release from position 1, rod, right? You release from position 1. So you release from rest. So V, velocity of center of gravity, will be 0. Omega do not turning, so 0. Right? So T1 equals 0. So it's important in the test or final exam, if it's the value 0, then you need to write. Then position 2. Position 2, it was rotate at a certain angular velocity. Then the mass of center of gravity also move at the maximum velocity. Right? So here 0, then it swing up. So center of gravity or center of mass will move in the maximum velocity. So V2 you have. So kinetic energy, you have 2. One is from the rod. One is because of the moment inertia. So you have I omega square. Okay, so this is a bit special compared to particles lah. So rigid body, you always need to consider the second moment of inertia. Okay, then you substitute inside. Okay, now, okay, spring don't have kinetic energy one. Spring only have potential energy. Yeah, just take note. Right, so the rest you substitute. Right, M is given, V you don't know. IG you refer to the table. IG is this rod shape by the center. So it's, you will see in the table the G at the center. So you get 1/12 M D square or ML square, right, in the table. Then omega you don't know. Okay. Okay. Then you use kinematics diagram to relate your omega, like I show you on the whiteboard just now. So you refer from G to the B point, right? You still remember how we draw IC, right? Yesterday I showed you, right? You put the ruler to the velocity, then you follow your ruler. Okay, so that's why your IC is here, right? So IC to G, say a point G from IC, you get the velocity of VG, and it's rotating anticlockwise. Here we are referring to center of gravity. Okay, right. Why we use G? Because it's more easier. And angular velocity on the rod, it will be the same. Either this point, this point, this point, they will have the same omega. So we use G to for more simpler solution. And also, and we find Vg because the previous equation also we do not know the value. So we use kinematics to find the missing parameter. Okay. Okay. So again, you link V equal to omega R. So you have the R here is 0.2, the length is 0.2, and then omega you don't know, but you want to substitute in. Once you substitute in, your equation will become only one unknown, omega. Sense. Okay. So you will get T2 equal to something omega square. Okay. Then, okay. So once you have that, you put inside called the conservation of energy. For rigid body, you need to consider potential and kinetics. For rigid body, particles, it depends. But particles is also good to consider kinetic and potential. All right. Now, so conservation of energy, we only consider two types, kinetic and potential. So before kinetic 0, V1 we already calculate. T2 we calculate just now. V potential 0. So in this equation, you solve for quadratic equation. So omega equal to 4.8 radian per second, anticlockwise. Yeah, always important to tell the direction after you solve. Okay, make sense? Okay. Now, the next example, I think is the last one, I think. Right, now this one, homogeneous, this is means it balance, this is a balance, right? So mass is 0, so attached to a uniform 5 kilogram rod. So rod AB, again, rod again, right? So sometimes the question do not give you the position of center of mass, G. You need to go, when you solve rigid body, remember to find the G first. I'll put in the diagram, G, where is your G? Okay, usually the center of the object. Okay, so here, a release from rest, again the rest, when theta 0, so theta is here, 0, theta equal to 60, determine the angular velocity again. So when this one was 60, and then you release, right? So this one will roll and this one will turn to horizontal, right? So you're focusing on rod AB actually. So the motion of this one rotate to this one is clockwise. Okay, yeah? Right. So assume this row without slipping, again, the row without slipping. Ignore friction of the glide here, ignore the friction over here, and mass of the collar B. So the purpose of this rod is just tell you the velocity of B. The direction of B will go down. Then A will go where? Horizontal to the left. So you have A and B go down. Then use the IC method to find the VIC. Okay. So this one actually quite simple. The hardest part is you fail to, or you cannot imagine what before and what is after. So for this kind of question, you need to draw scenario before, scenario after. So this one is before, like 60 degree, you put in your diagram, and then you draw another one. What happened when it become flat or 0 degree? So you need to do 2 diagrams. Okay, so same, you calculate for potential energy. Potential, you need to give yourself a datum. Now when it comes to rigid body, datum will not give you anymore. You need to give yourself, you need to solve the question based on your judgment, right? So you set your datum flat. Normally it's a flat surface. Okay, so we set datum over here, and then this is diagram 1 is before, diagram 2 is after. Okay, so when we draw diagram, again, first thing we go is the force, the weight force at the center of mass, and then what else? This mass also, because the disk was given, right? So you need to give W for the disk. Then there are only 2 because it tell you to ignore friction. So there's no friction here, and this one was without slip. So you want to consider friction, right? So after, then you have weight on the disc and also weight on the rod. Okay, and then 60 degree, 0 degree. So again, important is to find the height before the gravity. So this one you can find based on right angled triangular. So here to here is 0.3. 60 degree, you're able to find. So this is sine 60. Okay. You can use the full row, but you are finding another point. So again, omega, angle omega is the same along the rod. So what information you have from the diagram? You focusing on the center of gravity, center of mass is more easier for your calculation. Because if not later, you need to find your IO, the second moment of inertia. If you find other place than from the gravity or from the G point, then you need to calculate IO already. IO equal to IG plus MD squared. So it's a bit longer calculation. You can still find from B point, no problem. Then it will give you velocity over here already. Then you add yourself one more unknown. Okay. So yeah. So this one tell you the position 1. Position 1 is here, is above datum, so positive potential. So V1 equal to mgh 1. 2 you know lah, 2 0. Okay. Okay. So 2 0, potential 0. Here you don't have spring, so no spring energy, right? Okay. This also always at the datum, so 0, no potential. Okay. All right. So kinematic diagram, when you want to find the kinetic energy, So when it becomes flat, right? When it becomes flat, so you know that before it start from rest, so kinetic you don't have. Even the second moment of inertia also give you 0 because no turning. Right? So T1, remember, important to write T1 equals 0 if the question mentioned start from rest. So you only look at final position. So final position, again, we use the IC method. Gravity will point down because the gravitational center of mass velocity will point down because the rod go down, right? So you will point down. And because this one rotate in a circular motion, so it's actually it's a circular motion. So your velocity always tangent to the curve. So that's why you can draw 90 degree here. Then this is radius. You take V equal to omega R, so you can find the omega. Okay. Okay. So okay. Since the rod is fully extended in this position, the disc is momentary at rest. So your omega number 2, this for the disc will be 0. Because when you become flat, the disc no longer move. Okay, so omega 2, this for the disc will be 0. VA, velocity at point A, will be 0. So it's not moving anymore. Okay, because it was fixed. This rod come here, it cannot rotate already, maximum already. So V also 0. For this, for the disc. Okay. Then for the rod, you just relate to V equal to omega R. Okay. So you link with the gravitational center of mass point. Okay. Just substitute the numbers. Okay. Then you can find the energy, kinetic energy after. So you have the rod component, you have the disc component. You have two objects. So you have the disc because the question asks you to ignore the collar motion. Right? So you calculate the rod and the disc. So the rod, you have the mass effect and second moment of inertia effect. So mg half mv square and half I omega square is for this. Repeat the same for this. Okay, so you put in everything. So the rod is doing something, but the disc is 0, 0 because it's at rest and do not rotate when it reach that position. Okay. Right. So example 6 is tell you that this is a composite body. It consists of two body. So you need to do analysis for the two things. When you do conservation of energy, you need to consider everything inside the diagram. Okay. So you substitute, you get the thing. So T2, you arrive at one answer. T2 equals something omega square. Then you group them under conservation of energy. Kinetic plus potential before equal to after. You put in all the unknown. You only solve for omega R. Sorry, omega. Okay. So tell you that T2 also can find by IC omega square if you want. It's a solution for that. Okay. Okay. With this, we conclude chapter 7 and also conclude this module.